Let me start by introducing Caleb White, the graduate student who did most of this work, and my Sandia collaborator, Humberto Silva. I will start with providing some context for this study. Why is it that we're using different equations of state for gases that comprise a mixture which is then shock accelerated? Describe the software that is being used, the methodology, present some results, and then discuss what this means and what lies in the future for this direction of research. The motivation for this study was largely provided by experiments that were run in the last 2 years at the University of New Mexico, where we took a mixture of sulfur hexafluoride and helium, shock compressed it, and measured temperature and pressure before and after the shock and the shock speed. And the interesting thing about these results is if you use either Dalton's law of partial pressures or Amiga's law of partial volumes to predict the mixture properties, and you use Rankin-Hugoniot equations to account for the shock, for post-shock conditions in the gas, there is a sizable disagreement between experiment and theory. And our assertion is that this disagreement is there because the ideal laws cannot account for the non-equilibrium post-shock behavior. But maybe it has something to do, maybe we just have the wrong equation of state. Shock tubes and generally shock acceleration of substances to study equations of state. This direction of research has a long history, and people worked with liquid nitrogen and with solid carbon dioxide and with argon, and interestingly enough there were some discrepancies between theory and experiment already found for that case, argon, and most recently helium and sulfur hex study, about which I just told you. So let's start with what we did with the ideal gas equation, PV equals to RT. You can dial in the compressibility factor Z to account for non-ideal behavior, PV equals to Z RT. And assuming that we have ideal non-reacting gas mixtures, you can predict their properties with either Amiga's law of partial volumes or Dalton's law of partial pressures. And actually, for a perfect equilibrium case, these laws should give the same results for the mixture, although they have very different assumptions regarding entropy. These are implicit assumptions because neither Dalton nor Amiga knew what entropy is in the modern sense, but if you use Dalton's law, it implicitly assumes that the gases are perfectly mixed and do not unmix, whereas with the Amiga's law, it's kind of the opposite. All the gases just politely occupy the same volume without properly mixing ever. So, instead of using the ideal gas law, which is what we did for our theoretical study in 2018-2019, here we are using several different equations of state. The first one that we use is Becker-Kistiakovsky-Wilson equation of state, and here it gives you some way to dial in the compressibility factor Z, so that PV over RT equals to Z, which is shown here. And with known parameters, this essentially is based on co-volumes of products, say, after detonation. The other approach that we use is with Jacobs-Coppert-Waite-Zwisler equation of state, and this equation assumes an exponential order 6 potential for the intramolecular forces. And another variation of this equation is exp6. So here in the exponential you have parameter eta, and you also have it in the order 6 term. And for the original JCZ3, this is a constant, and EXP6 uses a non-constant value of eta. Let's talk about the software implementation, starting with the framework, Dakota, which is a design optimization, parameter estimation, uncertainty quantification, and sensitivity analysis, multidimensional parametric study framework, which wraps around arbitrary software. So, what do we wrap it around? First, we have a thermodynamic equilibrium code called Tiger, which can generate custom tabular equations of state. For modeling the shock, we use CTH, which is multidimensional, multimaterial, large deformation, strong shock, strictly speaking, solid mechanics code. What's nice about it is it has tabular equation of state input capability, so you can import equations of state tabulated by Tiger into it. And BCAT is the CTH distribution package that we use, and it develops and tests equations of state models, and it can use Tiger equations of state. This is how it all blends together. Now, to do the modeling, we start with generating equations of state for helium and sulfur hexafluoride using Tiger. We create mixed equation of state via summation, and we can do it using omega formulation or delta formulation. And during the CTH modeling, we model the geometry of our shock tube that was used to run the experiments at the University of New Mexico in the last 2 years, with some simplifications. So here we have a round driver section and a square cross-section driven section, and we have a diaphragm initially separating both of them. So we don't do any of this modeling. We simply scale the length of the driver section to maintain cross-sectional end area and volume that we get in experiment, and we don't account for the diaphragm at all. With these limitations, however, we model the rest of the experiment. We drive our computational shock tube with nitrogen at 3 different initial pressures. We put in the driven section, the helium-sulfur hexafluoride mixture at 3 initial pressures, which gives us a matrix of 9 pressure ratios between the driver pressure and the driven pressure. And on top of that, we also model 2 molar concentrations, 50% of helium and 75% of helium, same as we did in experiment. And I forgot to mention, when I said what else we use to simplify the modeling, we have reflective boundary conditions. So during the simulation, we parameterize 108 simulations in parallel with Dakota. And within every simulation, we run a Python script that performs the following tasks. You generate the input deck for Tiger to create the tabular equations of states. Create mixed equations of states for the appropriate molar ratio. Generate the BCAT input deck, and then generate the CTH input deck and run CTH to do the shock tube simulation proper and extract the scalar quantities of interest. Let's talk about the results. As you can see, here is the comparison of the shock velocity on the horizontal axis as the function of pressure ratio, that's the ratio between the driver section and the driven section pressure, so 9 test cases, same as an experiment. Stars denote the experimental values, and the interesting thing here is that regardless of the equation of state that we use and the equation that we use to create the mixture, all of these data points land pretty much smack on top of each other. They are these little circles, and they're all very consistent with each other, and they are not at all consistent with the experimental results, not anywhere near the interval of experimental uncertainty, which is actually so small that you cannot see it on this plot. Same thing happens for shock pressure. So the numerical model overshoots very consistently the post-shock pressure and undershoots very consistently the post-shock temperature. And here you can actually see these experiment intervals of uncertainty. So again, the disagreement is outside the experimental uncertainty. So what is going on? And we are working with relatively weak shocks, Mach number up to 2. Here I provide a link to our experimental paper, and the discrepancy is too prominent, so replacing ideal gas equations with some other equations of state does not fix it. So this theoretical framework simply lacks the necessary physics to capture the non-equilibrium post-shock effects in the relevant time frame. And what needs to be done is, first we need to conduct new experiments and to develop a database of other gas mixtures to figure out what is happening, and probably use molecular kinetic theory to develop appropriate models for the post-shock behavior. That's it. Thank you.